and measurement. So basically we have discussed about in the previous session about capacitive sensor and measurement, right? So, but we have introduced the principle and configuration, and capacitive sensors are utilizing the capacitance change between two or more, not necessarily only two, can sometimes be three conductive electrodes separated by the electric environment. And then the three can be changed, the distance between the electrodes, the interacting area, or the dielectric environment itself. That can be changed by environmental parameter, either displacement, humidity also. And then it will be changed into voltage, frequency, or pulse width variation. Okay, so these are based on the formula of the capacitance here, C equals to epsilon A divided by D. And this is when we vary the distance between the two plates. So the capacitance change is nonlinear, something like this, because it is proportional to the inverse of the distance. Then when we change the area, it will be a linear negative with negative gradient, okay, because the as we derive here, when we displace one of the plate relative to the other, it will have this linear change of the capacitance. Similarly, when the epsilon is changed, for example, by the movement of the dielectric medium between the two electrodes, then also it will change the capacitance linearly with negative gradient. So capacitance can be changed, capacitance change then can be converted into voltage or frequency or pulse width modulation using secondary transducer. Yeah, we have discussed this circuit in the previous session. You can use 555 base oscillator and then counting the resulting frequency. You can use this Smith trigger, a Smith inverter, is an RC oscillator also, whose voltage later, the output voltage will depend on the value of the capacitance here, which is basically the sensor. Then we can also use this synchronous demodulator circuit, where the output voltage depends on the value of the two capacitance here. Either both of the two can be sensors or just one of them sensor. The other one is a variable capacitor used to nullify, to calibrate at the beginning. And we have also discussed in the previous session some example of capacitive pressure sensor, of its application, yeah, of capacitive sensor. This is one famous example, of course, the use of capacitive sensor as pressure sensor. So instead of measuring the strain, like in the resistance-based sensor, I have actually explained about pressure sensor using resistance change. But now we immediately measure the capacitance between the two electrodes, between the fixed diaphragma and the moving diaphragma. As we know, as we can see here, the configuration is simpler compared to resistance-based sensor. In resistance-based sensor, you need these four sensors being attached to different places in the diaphragma, and they are connected through this Whetstone bridge. While in capacitance sensor, you don't need that. You just measure then the capacitance change. Here is the detail of the circuit. Then this is a modification of that capacitance-based pressure sensor using mercury ball to increase the sensitivity, because then the ball it is measuring basically the formation of the droplet here, either it is as the mercury, it is flat, or droplet, which will depend on the pressure of the external atmosphere. This is the table. And we have discussed also about flexible capacitive pressure sensor using polyimide-based substrate, polyimide polymer, and gold as the electrode here. The gold is just being coated as thin film, so it doesn't cost much per unit of the sensor. And PDMS also as the flexural, as the flexible material. Then The application of this can be used as flexible capacitive pressure sensor to measure the cuff, the cuff in nerve, to measure the health of nerve tissue. Then I think we stop here in the last session. So in this case, then you would use the capacitive sensor as an electrode microphone. Electrode is basically a dielectric material which has been electrized or polarized, where the charges are moving to different direction. Positive charge moves to one, and negative charge to the other direction, and that's why it is called an electrode. So this is the model of the electrode microphone. The membrane will be the one that is affected by the pressure due to the air vibration. Basically, a microphone here measures the vibration of the air, right? So vibration from acoustical point of view is the change of the air pressure due to the sound that we generate. So this will make the membrane to vibrate, and therefore the value of E1, the field between this membrane and the electrode, will also change. And this can be then detected, the field, by using this one, the field effect transistor. Another application is for tactile sensor. Tactile sensors are sensors that used to measure the touch. So basically, in terms of biomechanics, we know there are two types of sensor, tactile and haptic. Haptic is related. Tactile is more on touch sense. Our touch sense is tactile. Especially our finger, for example, has hundreds or even thousands of sensory neurons attached to the surface of the skin in the finger, right? And this is actually being mimicked by many researchers, that they develop this kind of an array of capacitance. So when you see here, each dot here is basically indicates capacitance and can be addressed by using this multiplexer, two multiplexer, to address the x-axis and the y-axis. So this will scan, similar like in screen, in TV screen, scan in the x-axis, scan at y-axis, and at one particular time, it indicates the pressure at one point. So by scanning at several milliseconds, maybe, and it can then give the capacitive map of the whole thing, which indicates then the pressure map. Because when we touch, when we touch with our finger, basically there are pressure map. The pressure across this surface of the finger is not the same everywhere. Some has higher pressure, the other one has more slight lower pressure, etc. So here is this usually can be used for robotic application. Okay, we have videos here. Let's see. We can I'm sure if the video doesn't work. Yeah.
Hi, I'm Joe Romano, PhD student at the University of Pennsylvania, and a summer intern here at Rural Garage. I work this summer focused on having the PRQ understand tactile information. Using tactile information, we were able to make the robot delicately grasp and manipulate objects, place objects down, and detect contacts between the robot arm and the environment. Previously, without tactile feedback, strong robot joints could crush many household objects and be unaware of unexpected contact events. Using sensors in the hand of the robot, we're able to do delicate and responsive control of the PRQ gripper. The robot is able to close its hand around objects in the world, recognize the moment of contact, and stop quickly before damaging the object. During manipulation, the robot detects objects slip and increases the grip force to stabilize the grasp. When placing objects down, the robot detects contacts with the table through its tactile sensors and gently stops its motion and releases the object. We have found that tactile information is also a useful role in handing objects to a human. When the robot has decided to hand over an object, it is able to detect when the object is being pulled from its grasp, a natural signal to release the object. Tactile information has also been integrated into the robot's motion planning algorithms. It's now capable of recognizing when it has made unexpected contact with the environment, stopping to avoid further damage to the contacted object and the robot itself. PR2 is now capable of detecting and responding to tactile events in a fast and natural manner. This work was done at Willow Garage with the help of Peter Niemeyer, Aikin Zhao, and Sachin Chera. Further code and documentation is available at ross.org.
Okay, I hope this gives you an idea, yeah, that this sensor, tactile sensor, can be used for robots. So we are not only working with for human also, but system that for human we can mimic and then develop an artificial robots like this, yeah, that can mimic the use of our gripping. Yeah, we thought that tactile sensor, the robots will grip with, we cannot control the gripping force. Yeah, so this is something which maybe you take it into granted. Yeah, when you when you hold your phone, when you hold eggs or food, sometimes you don't feel it, but actually your sensor in your finger detect the correct amount of force that needs to be exerted in those different objects. Harder object will require harder force. And how do we detect it? Using the sensor in our fingers. Okay, so this is what is being mimicked here. So the sensor are made using this pressure sensor array. It is made using surface micro machining, yeah, like this. Two membranes, two electrodes. They are very slightly spaced between each other using the surface micro machining. Yeah, using a small cavity here, and then it measures the deflection of this membrane. So it can also then be used, this one of the application of this array of capacitive sensor as fingerprint sensor. Yeah, actually your smartphone here applies capacitance-based. Yeah, that's why the touch sensor, yeah, it applies capacitive sensor as well. It has this multiplexer at x-axis and y-axis to measure the movement, the pressure of the screen at different location. So this is one application. So here we can detect the fingerprint by the different pressure applied by the finger on the sensor array. So here this is application of capacitive touch sensor.
Mechanical buttons fail frequently in wet, dirty, dusty, grimy environments such as factory floors and cooking ranges, as well as with outdoor applications such as electronic locks and elevator panels. MSP430 MCUs with Capacitance technology can be used to implement metal touch solutions, allowing highly reliable and elegant buttons, sliders, and wheels. Touch-through metal is inherently waterproof, dirt-proof, and operates while wearing gloves. Capacitance technology offers the industry's lowest power, versatile, noise-immune capacitive touch solution with an ecosystem that can have you designing your system in less than 5 minutes. In a traditional capacitive touch design, the touch sensor is connected to an MSP430 MCU and emits an E-field. When a human finger comes into the E-field, a change in capacitance is detected and a touch is registered. This mechanism works well with plastic, glass, and other non-conductive overlays. In the case of a metal overlay, the sensor E-field is destroyed, making it unusable. MSP430 MCUs with Capacitance touch technology uses an alternate approach for metal overlays. The stack-up comprises of a PCB with sensor electrodes, a spacer, and a grounded metal overlay. When a user presses the overlay, the metal bends, causing the air gap between the plate and sensor to reduce. The Captivate peripheral measures the increase in capacitance and detects touch. The sensitivity of the Captivate peripheral detects plate deflection at the micron level. Based on the force and amount of deflection, designers can implement features incorporating pressure sensing on the buttons. The Captivate Metal Touch plugin board can be used with the Captivate development kit to evaluate touch-through metal designs. Both kits are now available on the TI store.
This is made by Texas Instrument. Yes,
TI.com/captivate. Thanks for watching.
Okay, so that will be all for the first session, and let's have a break.